I'm going to start sharing the screen. Okay, so thank you for your dedicated effort to the lab yesterday, and thanks to Raju for sharing link to the video mark. So I hope everyone will be able to complete the video and send a link to the videos that you have composed. If there are some technical difficulties, please send me an email so that I can constructively contribute. The main goal by now is to prepare the slides for the presentations. We did really great last night, especially with thermal heating, and I think it is a good progress on movies. The only sections that are not covered are momentum dispersions, anions, cations, and spin polarized density of states. So the class materials are going ahead of the lines. The material on spin polarization was already presented in class. There is a little thing that will be gluing together the chapter on DFT that we are finishing now and the chapter that we will immediately start after everyone is after everyone will complete the presentation of VASP skills. So I will make an overview and maybe some reminders of what we covered by now, but the goal of the meeting today is excitations. So generally, density functional theory is not a primary tool for excited states. In case one needs to consider excited states of a material or molecule, one does need special tools, special theories, and there are multiple advanced theories for excited states. The simplest of them is so-called TD-DFT that I intend that we cover in the last chapter. However, in the very approximate way, the excited states can be covered by regular DFT, and if we discuss the way how density functional theory can approximately address excited states, it will be a good start to the next chapter. Okay, there is another goal, another plan that we should keep in mind. very soon we will start individual research projects, and there will be key step that we all will maybe I'll bring us to the step on coming Tuesday. We all should review opportunities of what to research and make selections, same as we did practice of democracy and election for subject of presentations in all two completed and one coming session. We need to vote on which research subject we want to present. So there is no time today to do so, but tentatively on Tuesday I will give a list of possible subjects, explain the pluses and minuses, and everyone will be welcome either to offer his or her own research project or accept one from the list. Okay, those were the plans. So it is a little bit too early. I'm going ahead of materials and my own thought, but let me bring you a little heads up what will be the subject of projects. This is just a little heads up information. We will go over the following thing in details again and again. So the plan for research projects is to explore the role of thermal motion, or maybe transformations, chemical transformations induced by thermal motion onto electronic structure. So the suggested, of course, research is a very creative procedure. There are no strict steps how to complete the research, but there is a tentative flow chart. So one is selecting a model that you want to pursue, optimize geometry, and then for the optimized geometry find properties of the interest. In a basic way, it is density of states and spectrum, but they can be different observables. Then one takes the model and explores it with thermalization and molecular dynamics. Not necessarily at room temperature. One can get some crazy high value temperatures like 2000 Kelvin. It will be dependent on the nature of the project. And then at the last step of the dynamics, one can use geometry of last step, rerun single point, and then look how density of states and spectrum changed upon this thermal motion. And then one can verbally and intellectually compare these two sets of data and make conclusions how the thermally induced transformations modify properties of this and that material. Other questions to this general direction right now? Okay, I don't see questions. Okay, let's begin. It's review. So before we go to the excited states, I will just bring up a couple of slides that from our last meeting that we have completed. So By now, this information about spin polarization is a primary interest of Rebecca, who volunteered to present on spin polarized density of states. But there are two independent sets of orbitals with spin up and spin down. Highest occupied is different for alpha and beta if it is magnetic material, and this determines spin unconfined spin multiplicity. For running for density functional theory working in these circumstances with unpaired number of spin up and spin down, one introduces spin polarization density and composes the and one composes the density functional out of total density and alpha and beta spins, which are expressed through the spin density. And this is the last slide from our last meeting. This is an example of one of the GGA functionals. In a month from now, when there will be final presentations on research projects, there will be visitors. I hope there will be visitors to these presentations, and if any of them will be from the community of computational chemistry and materials theory, there will be a question to presenters: which functional did you use in the simulation? So, and maybe some of you already want to ask me what we are doing in the labs. So in the calculations that we are practicing during last couple of labs, we are using PBE function, which is belongs to the GGA family. And I'm not giving the equation for it because it will be much longer. Okay. So here is the flow chart of DFT borrowed from another source. I think the one that we used in the class and that you have contributed by copy pasting equations inside is better. This is just taken from one of the sources. Just a second. I want to show something to Amir. There were questions on the books that is appropriate for DFT. So this is quite simple. It doesn't for quantum chemistry. It's part of the physical chemistry, and I can type it. I doubt that anyone wants to read it, but just in case so that you have the source and some information, you're welcome, that we discussed in the class is originating from this book. For example, this page on local spin density and GGA functions. Okay. Going back to slides. So it is a little bit different form of expressing the DFT flowchart, but you recognize that it is the same. So we in this example, one skips introduction of initial ionic coordinates, and then one does have the initial density. Since this was created by physicists rather than chemists, there is in respect to DFT, there is only one difference between physicists and chemists. Chemists write letter rho for density, and physicists write letter m. its starting density, and then through the functional, which depends on the density, one gets to the CHEMM676 equation, composes the density as summation of all occupied orbitals, checks if system is converged, and then gets total energy. And the only thing that differs in different implementations, different codes that one can change by running DFT is the equation for this CHEMM676 potential or the equation for total energy as functional of the density. Okay, so here we have this CHEMM676 equation, and here is a general way how the total energy is composed of the density. We already covered it in the class, so I'm showing it just so that you feel more comfortable if you see similar equation in the books. So the kinetic energy is expressed in terms of orbitals with the gradient, and then there is a Coulomb term for repulsion. Then there is a interaction with external potential, basically interacting with ions, and then another part of electron-electron interaction, the exchange and correlation are stored in this symbol, and a lot of authors prefer to chop the total energy in these terms. So please do not focus, lean back and relax. The information that I'm showing right now will not be used for our practical calculations. It's only if you have a lot of curiosity and if you plan to read literature related to density function theory. So those people who design and explain functions, which means connection between density and total energy, do accept set of standard notations, and the equations for total energy typically use these notations. So Wigner-Zeitz radius, which is inverse of the density, spin polarization, the momentum that corresponds to Fermi energy. So we cover this concept in Thomas Fermi theory. So what is the momentum of the electron when it is in the highest occupied orbital? Then the gradient of density expressed in the dimensionless form. Then the total energy that would come from Thomas Fermi theory, if one would need it. This symbol tau is local kinetic energy, which is expressed as gradient of wave function, and this corrections for local kinetic energy is the next level after GGA. And this notation is in one of the approximations. It is what contributes to the exchange. It looks very similar to LDA expression. Okay, just for curiosity. And here is another example of GGA function. So typically people who work on designing functionals try to call the functional after their names, and if you drop down menu in Gaussian, you can see some of them, and when it will be time, I can share the template in cards for each of the specific function. So GGA typically has total energy from LDA as a starting point, and then there are corrections, and it is not pleasant for humans to read, but if someone really needs to explore this equation, here are the gamma is parameter, and this hyperbolic inverse hyperbolic sine is this function. X is dimensionless gradient. So I do not think we will do research on equations on these equations, but the only goal is to avoid fear, so that we do not feel scared if you see equations like that in the books or in papers about DFT. So in some sense, we are starting the new chapter, or we are making preliminary steps towards starting a new chapter. And before we go to true methods and theories designed for the excited states, I suggest we squeeze as much as possible all maximum useful information from the ground state method. So DFT is often called ground state theory because DFT, as well as Hartree thought, is one of the ground state theory. I'm going to temporarily migrate the to look at the communication software and ask, do you have an idea why the DFT is called is referred to as ground state theory? I believe you have, if you want, you have enough background information to answer this question. Let's try.
Because the geometry is optimized.
No, it's a good try, but let's think not about geometry, but about orbitals, their occupations, and okay, and let's try one.
Because we want to find the energy when the molecule are relaxed. The potential energy surface at the minimum energy point.
Okay, so in some sense, Raju, you're correct, but one needs additional disclaimer. So yes, we are looking at the minimal energy, but minimal energy of a sense that we found, if DFT did work out for us, we found such density, such orbitals, such that will give minimal energy. So original goal, although we are doing geometry optimization and molecular dynamics, the theorems are speaking about geometry being nailed down, and the only parameter is the shape of orbitals and shape of the total density. So who else wants to try verbalization to verbalize why DFT is ground state theory? Amir, I see your microphone is on.
Yeah, but I'm just thinking.
Okay. So how do we compose density out of the orbitals? We do add together we do add together absolute value square of each orbital, right?
Yeah, it's normalized.
All orbitals, but how many orbitals do we take into account for composing density? This question is not challenging. So suppose we have a model with 4 electrons. How many orbitals will be used for the composing the density?
2.
Yes, if there is no spin, 2 orbitals. If they are spin polarized, 4. So in order to compose, and how do you select which orbitals? Can you use orbital number out of this 2? Can you use
from the ground state?
Yes, Salim, perfect. So we are going Aufbau principle. We start from the lowest and fill it with electrons. We are not doing like orbital number 10 and orbital number 20. We're using only orbital number 1 and number 2. So in the DFT protocol, the original DFT protocol, we use lowest, we use only occupied orbitals, and we occupy orbitals according to Aufbau principle. So we set electrons to orbitals to describe the ground state. Therefore, density functional theory is referred to as ground state theory. So using DFT for excited states is not ideal. It is an approximation, but I suggest this step only as maybe pedagogical, educational step, because we do not need to learn new theories, and we just expand the borders of applicability of the theory that we got. So I will probably insert new slide and just write things down. It will be the best thing. So the density is composed as summation of all orbitals from the first I equals 1 to the last occupied or highest occupied, and then we take the this orbitals star at point R, then orbital without star at point R, and that's it, right? Please object if you do not like this equation, but I think everyone agrees because it is what we used when you were moving equations through the screen for building the algorithm, right? Now, I am going to make a little trick to write the same equation but in a different form. What if I want to set summation in this equation not until HOMO but until infinity? Can I do this way? Theta star I theta I without star. Are the pink and black equations equivalent?
I think that they're only equivalent when there is no electron in the excited state.
Okay. Okay. And what should I do to make them equivalent? So I do want to run summation over from 1 to HOMO, right? And I want to disable summation above HOMO. Right? So what if I'm putting here the factor I, and I will put like comma and tell f equals 1 if I is less or equal than HOMO, and f sub I will equal 0 if I is bigger than HOMO. Do you like this explanation? Do you like this equation?
Yes, makes sense.
Okay, so please object if you do not like. I will consider silence as support of this equation. Okay, so we do have an equation that combines all orbitals, formally, mathematically combines all orbitals into density. And the only specifics is that we are putting a weighting factor that disables the contributions from undesired orbitals, right? And if we set up a little figure with f sub I on the y, and we will put I on the x-axis, 0, 1. Then up to HOMO, the values, values of this f factor will be equal 1, or it can be 2 if we have no spin. Right? And after HOMO, they will be zeros. Make sense? Okay, good. So, if I will make a trick and remove an electron from one orbital and place it into another one, this will be a very, very rough and approximate description of the photoexcitation. When I remove the electron from occupied orbital and place it into the one of the unoccupied. And such modified F factor can be used as an input for DFT procedure to compose the density. So let me check who will be. So Mahek, are you in?
Yes.
So
Yes.
it will be the third, like you will present three small sub-subjects: anions, cations, and excitations. So
Yes.
for excitations, it is basically this thing. And there is a command in the in-car that manually sets up the values of this factor. So this factor is originally set up to Fermi distribution, but if you want to manually modify it, you are adding the following command in the in-car. Fermi weight. And then one is writing 1, 1, 1, so many times 1 as many occupied, and then 0, 0, 0 as many as there are unoccupied orbitals. But if one does want to describe a ground state, one may replace one in the one value in the occupied domain and one in the unoccupied. Make sense?
Yes. So this is the excited state, right?
Yes, excited state. So we will practice it on the coming lab on Wednesday, but I want to give little heads up.
So in VI in car we edit this.
In the in car one needs to add this line, and I will show it. I will provide a template so that you do not waste time of typing too much.
Okay, thank you.
Yes.
So I have a question.
Yes, please.
Is the electron close to the HOMO, would it be the most likely to be excited and go to?
So in your quantum dot research, you can excite quantum dot with light of different wavelengths. So if you excite it at the band gap energy, then you will promote electron from HOMO to LUMO. But if you excite it with UV, you can promote it from like HOMO minus 10 to LUMO plus 100. So selection of the orbitals that you modify occupation depends on the circumstances of your scientific research. Like if the higher the excitation, the larger the number of orbitals that you perturb. Okay.
Because that would mean that the energy is high, right?
Yes. Yes. Correct. Yeah. Many thanks for bringing this up. So
thank you.
My pleasure. I want to insert one more slide because the one that was pre-made is a little ugly in its writing. So on the previous slide, we were composing density by making summation of orbitals theta I star theta, and we had a factor f. So before on the previous slide, we used to have the same index for each of this object. We were running summation on only over one index I. But I'm going to get crazy. There are no mathematical theorems telling me that indices must be the same. mathematically, I can put different index, I and j, and then then here the weight factor will be also I and j, and we will have two summations, one summation over I, another summation over j. And maybe a lot of people call it then not f but rho. So I invite you to stare at this equation and express your protests. Like, please tell me why you dislike this equation. What is ugly? What is strange? What you do not like? Raju?
Can we use it as a bracket function? Because
please repeat.
Bracket function, in bracket function there should be same, right?
Orbitals, yes, orbitals must be the same. Yes, if we want to use it to regular ground state DFT, then this indices must be the same. Good. And if we want to stay within regular DFT, we still can do it. We can tell that the factor I j will be equal 1 under certain conditions. If I equals j, and if both of them are smaller or equal than homo, right? And in all other cases, it will be 0. So if I is not equal j. So under such condition, we still can use this double summation. Okay? But this equation is introduced intentionally. It will open us a door into excited state theories. So it will open us an possibility to describe fine details of excitations. So I'm not going into these details right now, only focusing on the notations. So how do we call the letter rho at the leftmost part of this equation? Jean-Fan?
Density?
Yes, correct. So it is density. Thank you.
And Dr. Kenny, I have a question.
Yes, please.
Is there any physical meaning if I doesn't equal to j?
If I does not equal to j, it will.
Yes.
Yes, absolutely. And it is what I'm going to tell. If you let me speak, I'll complete the thought. But since you're curious, I'll give you the keyword right now. It is transition density, if I is not equal to j. Now, so the density on the left is continuous function depending on position. Right? And here we have orbitals that depend on position, and also they are specific for each index. And the object with indices here, it is discrete, right? Because it depends only on indices. Discrete. So it is an object a set of numbers with two indices. What is the typical name for a set of object for a set of numbers with two indices? Like if we have this previous one, fi, it was values 1, 1, 1, 0, 0, 0. It was like a vector, right? And if we do have an object ij with two, what?
It should be a matrix.
Yes, yes, thank you. Very correct, very true. Yes, matrix. And this matrix is related to which physical quantity? This is a matrix that help us to construct density out of orbitals, right? It is related to density. So the good word for it will be density matrix. Okay. I hope you like this naming and this definition. So we can construct density out of orbitals by using density matrix. In case we are describing ground state, density matrix is diagonal, has only values when I equals j, and only non-zero values for orbitals equal or below HOMO. So here is the same equation from previous years, and here how the density matrix looks like for the ground state. So for ground state, there are non-zero values along main diagonal only until HOMO. Until indices, both I and j indices take value of HOMO. All other elements on the diagonal and away from the diagonal are zeros. So by now, it may look crazy, like too many notations, too many symbols for a simple thing, for the ground state. But if we set up a target to describe excited state, then we need both opportunities, both directions of modification. One, we need the ability to promote electron from occupied to unoccupied orbital. And in addition, we need to look deeper into this process. So if we look onto mechanics of how this transition is happening, not only initial and final state, then the process of interacting between molecule and light will create non-zero elements in this off-diagonal domain. So if the system is experiencing transition from ground to excited, it's not only repopulates originally unoccupied orbitals, but it also develops non-zero values corresponding to transitions. So as soon as we define density matrix with two indices, we are starting to depart from ground state density functional theory. We are on the way to design new theory, which will be more general, which will be available to describe repopulation by excitations and the process, how this repopulation happens. So this little equation is what is used in VASP when we are in the ground electronic state, but the temperature is non-zero. So one uses Fermi distribution, and it is electronic temperature that one is using in MD. So if Raju was asking this question, like if a system has small gap and you are looking onto the states file, there is 1, 2, 3, and HOMO, LUMO. There are energies like -20, -7, -4, and populations here go 2, 2, and then for highly excited states, the occupation will be 0. But if the model has a small gap at large temperature, here the values will be, instead of 2, it will be like 1.6, and LUMO may have like 0.4. So if you were looking into the states files, you may have observed this feature of occupations deviating from integer numbers. And this is the consequence of Fermi-Dirac distribution. In other academic courses, this distribution appears in the statistical mechanics and physical chemistry too. Fermi-Dirac. Okay. So, are you tired? Do you have energy to absorb a little bit more new information? I have only 3 slides, and we'll stop there. So let's chop our density matrix on segments. So the summation of the indices, the values of the indices in this double sum can be run in 2 segments, from 1 to HOMO, either for first index or for second index, and then it can be run from LUMO to infinity for one index and another one. And summations for first and second index do not need to coincide. There are situations when one index is being run in the smallest values of the indices, and another in the largest. Please object if you do not like this notation or if I need to explain it more. Jean-Fan?
Yeah, it makes sense.
Okay, thank you.
I think so can we just replace the sum from 1 to HOMO by just 1?
No, because there are several orbitals from between 1 and HOMO, and we need to take all of them into account. If we would describe like molecular hydrogen, H2, or like hydrogen atom, then yes, there will be only one orbital, and we will call it HOMO. But for real molecules, there are several occupied orbitals, and we need to design theory that is able to describe it.
Okay, I see.
So the segment in if summation in yellow, it means we will go only over the domain of indices that correspond to occupied orbitals. if both indices are above LUMO, we are going to the domain of the unoccupied orbitals. And in case we have this mix and match, I don't know how to show it, maybe just doing stripes. If you have both green and yellow, it will correspond to the off-diagonal segment of density matrix. Now, for the overall density matrix can be chopped onto 4 pieces. The piece that corresponds to the domain of occupied orbitals can be called ground state. Or because there are 2 indices, we can call it ground, because index 1 is ground, index 2 corresponds to ground. The segment where both are excited, we can call it EE. Both are excited. And when we are looking for a transition between ground and excited, we can call it GE, ground excited, and EG. So this chopping of the density matrix of segments is needed to develop a useful language to speak about these processes. So when we will be doing little tricks in VASP to use ground state DFT, the third part of the Mahek presentation, we will modify only the diagonal of this density matrix, and we will affect only GG and EE. But if you want to make a true theory for excited state, if you want to explore mechanics, how the transition from one state into another one is happening, we do need to describe this GE and EG components of the density matrix. So this EG and GE components are intentionally referred to as transition density matrix. Transition density matrix. And in case if we compute the density contribution originating only from these off-diagonal elements, if we remove the diagonal and keep only off-diagonal, then this will be called transition density. Transition density. So this terminology and these concepts are not my design, not my intent to make the course more complicated. It is very standard terminology, and anyone who goes for this computational description of excited states uses this nomenclature. So I'm just introducing it and bringing us closer to the standard notations. Okay, 2 slides more, and they will be less intense. So for the ground state, we have no GE, no EG, no EE, only GG. And the GG part of the density matrix comes from Fermi distribution. In case we perturb system with light of small intensity, the excited part will be still smaller than ground part. It will be much smaller, but the transition density will be not as small. So if one practices careful perturbation theory, the first thing that will experience change upon including interaction with electromagnetic field will be transition density. And in all theories, one often neglects the GG part, but intentionally focuses on GE and EG. Good. And going to the last slide. So the GG is big. The EG and GE are small, and EE are very small. The values of this transition density and excited density are linear and quadratic in the strength of electromagnetic field. So if electromagnetic field is small, like smaller than 1 in some units, then square is smaller than linear. Therefore, this part is smaller. So the goal of excited state theories, in narrow sense, is to find the transition densities. Okay, I think it is enough for today. I will stay here and answer any questions if there are some. But if there are no anyone without question is welcome to disconnect.
Thank you very much. Have a good day, Dr.
Yeah, thank you. Thank you. A nice weekend, and looking forward to see you on Tuesday.
Okay. Thank you. Have a good day.
Thanks.
Thank
Thanks,
you.
Ido. Thank you for your patience of going over many hard concepts. I know that, especially if you're doing experiment, there are concepts that maybe are not in everyday research life, but hopefully it will be useful for your project.
Yes, it definitely will. Thank you. Thank you very much.
Thank you.
Hi, Dr. Kelly.
Yes?
Thank you.
Does this video mark support the Mac system? So I couldn't find a video mark for the Mac.
Okay, I will. Please send me an email reminder, because I did solve this problem in the past, at least for my laptop, and I should be able to recall how I did it and suggest. Yes, video.
And I also checked the pop-on you shared to me, and she or he also used the Windows system for the VMD.
Please repeat.
I also checked the PowerPoint you shared to me the last year, and she or he also used the Windows system to install that software.
Okay, yes, I understand. I'll check how I did it, because I personally did it for the Macintosh.
Yes, okay, thank you.
Thank you.
Thank you, Dr. Dimitri. Have a good weekend.
Thank you, Roger. You too.
Bye.
Bye-bye.
Thank you.
Thank you, Mike.
Bye.
Bye. Mason, many thanks for the support, and have a happy Easter break. I'm disconnecting now.